Thanks to CuriosityStream for supporting PBS Digital Studios. It's 252 million years ago, and the world is on the cusp of the worst disaster it would ever experience. 70% of all life on land is about to vanish, but one of the very lucky and very few that will survive is an animal called Synapsidoen. It's about the size of a fox, and it's a strange creature full of contradictions. It doesn't stand upright like a mammal or sprawl its legs like a reptile. Its jaw is full of specialized teeth like a mammal's, perfect for capturing and chewing up insects and other small creatures. And its nose is more mammal-like than lizard-like, but it doesn't have the soft ears that mammals would have. It looks like a creature in transition, which is exactly what it is. Synapsidoen is a synapsid, a group once called mammal-like reptiles, but who are now more accurately known as stem mammals, and they evolved in the peculiar conditions of the Permian period. Synapsids were the world's first ever terrestrial megafauna, with carnivores that grew to the size of bears and herbivores that reached 2 tons. But the vast majority of these giants were doomed to extinction. Almost none of the synapsid lineages survived the extinction at the end of the Permian, known as the Great Dying, and their legacy would be soon overshadowed by the Mesozoic age of reptiles. However, Synapsidoen and its relatives rallied. They lived on, thriving in the Mesozoic while keeping a low profile among the dinosaurs. And it's thanks to these unassuming survivors that the synapsids would eventually culminate in what is arguably the world's dominant form of life on land today, the mammals. Many of the adaptations that these forgotten ancestors acquired way back in the Permian period still persist today, in you and me both. So more than 250 million years later, our world is the way it is because of the time the synapsids struck back. During the Permian period, something big was happening on Earth. Its land masses were forming a supercontinent called Pangaea. And Pangaea would become the biggest unbroken stretch of land in the history of animal life. Its massive size would change the climate on dry land by reducing the moderating effects of ocean currents that kept some parts of the land damp and cool. As a result, throughout the Permian, deserts would spread and the world's climate would become much more variable. But in the early Permian, humid tropical swamps still straddled the equator, and in lush forests dominated by ferns and ancient plants, a new kind of tetrapod was taking over, the amniotes. Amniotes first appeared nearly 315 million years ago in the Carboniferous period. And unlike the amphibians before them, they could likely lay their eggs on land. This made them less dependent on water and opened up new terrestrial niches, something that would really come in handy for life on a big, dry supercontinent. And the amniotes quickly split into 2 branches around 310 million years ago, one that would give rise to all reptiles and birds, called the Sauropsids, and the other would eventually give rise to the mammals, the Synapsids. The difference between these 2 groups was initially small. Synapsids had 1 pair of openings in the skull called a temporal fenestra, while the Sauropsids had 2 pairs. But these 2 branches of land vertebrates would soon plot very different courses. While both groups looked a lot like lizards when they first appeared in the late Carboniferous period, by the end of the Permian period, synapsids had developed many traits that hinted at the mammals to come. Fossil evidence shows that early synapsids radiated much more quickly than their sauropsid cousins. By the early Permian, synapsids became much more common in fossil assemblages. It's hard to know exactly why this was the case, since members of these 2 groups still seemed a lot alike. And this early group of reptile-looking synapsids, known informally as pelycosaurs, quickly radiated to fill many different niches on land, including some that had never been filled before. In fact, pelycosaurs were some of the first ever large land animals, with species ranging from 3 meters to 6.5 meters in length. This growth spurt might have initially occurred because some pelycosaurs were adapting to herbivory. Pelycosaurs were some of the first terrestrial vertebrates to start eating plants. It required them to grow large fermenting stomachs to make the most of their high fiber and low nutrient meals. This rotund, barrel-like belly is on full display in the early herbivorous pelycosaur Cotylorhynchus, whose body dwarfed its tiny head. And these stomachs weren't the only thing that was changing. Plant-eating pelycosaurs were also adapting more specialized teeth and jaws that could crush, grind, and shred vegetation. Pelycosaurs dominated the land until the end of the early Permian, about 271 million years ago. They probably outcompeted the sauropsids by being more adaptable and specializing more quickly to take advantage of food sources. And many of them, like Dimetrodon, had large sails that suggest synapsids might also have been better adapted at regulating their body temperatures. By the middle of the Permian, though, conditions were changing, as they do. Tropical, swampy ecosystems started to shrink, seasonal temperatures became more variable, and deserts spread. Pelycosaurs needed an environment that was consistently warm and humid in order to survive, and they weren't equipped to handle the transition. But a new group of synapsids was the Therapsids. Therapsids were the second major radiation of synapsids in the Permian, appearing around 272 million years ago. By about 265 million years ago, they were the dominant group of terrestrial vertebrates. These synapsids had a number of traits that suited them to a much more active and high-energy lifestyle. And these are also some of the earliest traits that resemble those in mammals. For example, instead of having a row of teeth that were all the same size and shape, Therapsids had teeth with different shapes for different functions. Carnivores like the massive Ankylosaurus had large front and canine teeth for ripping flesh and smaller teeth in the back for holding prey. This trend toward more specialized teeth and jaws would continue to develop. Later carnivorous therapsids could even chew their prey rather than ripping off chunks of meat and swallowing them whole, like what reptiles and birds still do today. Furthermore, they developed a secondary palate, which redirected their nasal passage, allowing them to chew and breathe at the same time, which is something I certainly enjoy. Along with this secondary palate, some later therapsids developed features known as nasal turbinates, which are specialized structures in the nose that help animals take in oxygen more effectively. These two traits together indicate a higher metabolic rate. The shape of therapsid skulls also had space for more jaw musculature, which allowed for an increased bite force, and therapsids developed a more flexible neck, a longer stride, and a more upright stance. These changes indicate that therapsids had a more versatile range of motion than other land vertebrates, which made them able to move faster and more energetically. And being high energy is linked to another key trait that we associate with mammals: the ability to maintain an elevated internal body temperature. In addition to their physical adaptations, we have other evidence that therapsids were capable of basic thermal regulation. For one thing, their fossils are found in temperate regions that had cooler winters and hotter, drier summers. And researchers have also found hair-like structures alongside therapsid bones in the coprolites, or fossilized poop, of late Permian carnivores. This indicates that at least some late therapsids might have had hair, a key adaptation for insulation to maintain body temperature. And all of these traits show up in one particular group of therapsids, one that's of special interest to us mammals, the cynodonts. They weren't the biggest or the fastest, but that's probably what helped them get through the extinction event at the end of the Permian. These animals had the active, energetic lifestyle of other therapsids, but their small size meant they required less energy, which is important when you're trying to survive a mass extinction. Cynodonts probably also survived thanks to their ability to avoid predators and to keep a low profile. One way successful cynodonts like Synapsidoen might have done this is through burrowing. The oldest known example of a cynodont burrow is dated to around 251 million years ago, just at the boundary between the Permian period and the Triassic, when the Great Dying was coming to a close. And burrowing would come to be a quintessential mammalian trait. Today, at least half of mammal species are burrowers. Because of their ability to survive in more variable conditions, to use fewer resources than other synapsids, and to avoid predators using speed and stealth, cynodonts managed not only to survive, but to remain diverse after the greatest mass extinction of all time. And if they hadn't, you and I would not be here. After the vast majority of synapsids went extinct, the sauropsids had come out on top by the mid-Triassic. The age of reptiles had begun. Meanwhile, the descendants of those little cynodonts persisted through the entire Mesozoic era, hiding in the dinosaur shadows. So to this day, the legacy of those very first terrestrial ecosystems and the forgotten age of the synapsids lives on in today's mammals, including us. You, for example, have one pair of temporal fenestra in your skull because you, my friend, are a synapsid. You also have hair, specialized teeth, and nasal turbinates like some of our distant cousins, the later therapsids, had. And our closest synapsid relatives, the cynodonts, had these traits too, as well as the ability to regulate body temperature and a knack for burrowing, which you may or may not do. I don't know how you spend your free time. So you may not see the family resemblance between yourself and little Synapsidoen, but those features still connect you to that long-forgotten animal even after more than 250 million years. Thank you to CuriosityStream for supporting PBS Digital Studios. CuriosityStream is a subscription streaming service that offers documentaries and non-fiction titles from a variety of filmmakers, including CuriosityStream originals. For instance, you can now stream Ancient Earth, a 3-part series that chronicles the history of life on Earth from the Permian to the Cretaceous. You can learn more at curiositystream.com/eons. Thanks for joining me today in the Konstantin Hassas studio, and thanks to this month's eontologists, Jake Hart, John Ivy, John Davison-Ing, and Steve. If you'd like to join them in supporting us, go to patreon.com/eons and make your pledge.